So today we are going to discuss about a special kind of materials. So these are known as soft magnetic materials and hard magnetic materials. So when we discussed about hysteresis, so M versus H. So there are two possibilities in hysteresis. So one is, let's say, this is hysteresis with a large cohesive field, and then another possibility is with okay. So the hysteresis with large cohesivity is known as a hard magnetic material. So hard means it is difficult to, so you spend more energy to demagnetize it, or even to magnetize it. So you need higher field to saturate it. Also, if you want to demagnetize it, so you need also more energy. But soft, the other one is soft magnetic material. So soft because it is easy to magnetize and demagnetize. Okay, so you can easily magnetize it very quickly. So that you apply a small field compared to your hard magnet, so you can saturate it, and also you can easily demagnetize because the cohesivity is small. So this is the basically two different kinds of magnetic materials that are used in all the applications. So first we talked about the soft magnetic material. The soft magnetic materials are used mostly in, so like you might already know, transformers or motors or generators, or mostly, let's say, for high frequency application. So why it is the case? So the soft magnetic material, as we saw, that it has a narrow hysteresis loop. So this area of the hysteresis loop represents the energy loss. So this is basically the area is the energy loss. Now, smaller the area, so the energy loss will be small. So that means if I take a soft ferromagnetic material and I drive the hysteresis, so the energy loss in that process is small. So especially for this, when you apply AC field or a AC voltage source, so you can drive the hysteresis and then the loss will be small. And that's why they are all used in this transformer or motors or generators, or even if you go to high frequency applications. So let's take one example. Let's say take the example of transformer. So I think you might know how a transformer works, or a motor works, or a generator works. So we will not go into how that works, but we want to see what is the role of materials in improving their performance. Okay. So if I take example of transformer, the transformer, let's say you have basically this a core, this ferromagnetic core, and you have a primary coil, you have a secondary coil. Okay, so here I call this VP, and then this LP is a number of windings. So here I can calculate what is the output, which is the secondary coil, and here NS will be number of windings in secondary coil. So this is basically, it can work as a, so what is the basic principle? So you have a voltage here, so that will induce a flux in your magnetic core, and this flux will connect to the secondary coil, and that will induce a voltage proportional to the winding number and the flux, right? So you can have a flux phi, which is coupled. So this phi is magnetic flux couples the primary coil to the secondary coil. So there is no direct electrical connection, and that is how it can step up or step down the voltage and so on. Now, how do we define the efficiency? So efficiency is output for any device. So whatever is the input power and how much output we get. So which is, you can write it like input minus loss divided by input. So if you want to increase the efficiency of any device, doesn't matter, it could be a transformer or a motor or anything. So you want to reduce the loss. So the aim is to reduce the loss as much as possible. So what are the ways in a transformer that loss can happen? So what kind of losses you expect or you think can happen in a transformer? Anyone?
Heat loss.
Heat, yes, right. Core loss, that is true. So
Flux loss.
yes, eddy current loss. So you have basically core loss. So the loss due to your core material, right? So due to the core material, you have this, which is the magnetic material. So that will give rise to a loss. Of course, there is the heat loss, or known as copper loss, right? So this is again when you have the copper winding, so there will be a heat loss due to that. But we will look at only the core loss, because that involves our magnetic material. The core loss can be due to hysteresis loss, and due to this eddy current loss. Okay, so these are the two losses which contribute to the core loss. Now, what is hysteresis loss? So if you plot, let's say if I plot the energy loss per cycle. So remember, these are operating in a AC voltage, AC power. So I can calculate, let's say if you look at the plot of energy loss per cycle as a function of frequency. Okay. So the total loss will be something like this. So out of that, so this is my total loss, and then I have a hysteresis loss, and this is eddy current loss, and this is known as anomalous loss. So remember this, so hysteresis loss is due to your hysteresis, how the hysteresis loop is. And eddy current, why do you have eddy current? So eddy current is just because, so you have, let's say, you take your material and you have a winding, okay? So let's say if I say I have a current IW passing through it, so it will produce a magnetic field HA, right? And due to the changing this magnet, so this is frequency in the x-axis. X-axis you have, this is frequency. Okay, so frequency of the applied power source. So that will, so when you change this increasing or a changing current, AC current will produce or induce an EMF, so which is going to oppose the magnetic field. So we call it E. Is it visible? Yeah, HEC. Okay, so this will induce. So I can put it here. So it will induce a current in the opposite direction. Okay. This current we call IEC. Okay, so this is eddy current, and which will induce so this induced EMF will produce a current, eddy current, and a field which will oppose the applied field. So this is just from your Lenz's law. So that when you increase it, so it will produce a field which will oppose this HA due to the current. So this eddy current. Okay, and now when you look at the eddy current, the induced EMF. So how much is the induced EMF? The induced EMF in such a case is, so it will be minus d phi by dt. So d phi is your magnetic flux. D phi is the magnetic flux, so which will be equal to, you can write it down as dP by dt. Okay, so A is, let's say, your cross-sectional area, okay, and B is your magnetic induction. So this eddy current will exist for any material. So it doesn't matter whether it is magnetic or non-magnetic. Okay. But now, if when I look at this magnetic material, so I have B is equal to mu naught H. So my induced EMF is of the nature of PH by dt. Okay. So of course mu also depends on the applied field, but let's assume some. This mu is permeability. So that means the induced EMF in a magnetic material will be much higher compared to a normal non-magnetic material, because you have a factor of mu in it. So therefore the induced EMF will be high, and that's why the eddy current will be higher in a magnetic material. If you have a higher permeability, you have a higher eddy current. Mu I, that implies I is induced. So that means the loss due to eddy current will be higher in magnetic material. Okay. So the question is then, how do we minimize it? So that is where so there are many techniques. So you do this lamination. Okay. So instead of using just a piece of iron, you do the lamination, and then you introduce. So by using a lamination, so you reduce the resistance, and as well as to reduce the cross-sectional area of the current which is passing through, and that's how you can reduce the eddy current loss. But what is the role of a magnetic material here? So if you look at the plot I just had for the loss, okay, so for the loss we have a hysteresis loss, so that means if we want to reduce the hysteresis loss, so that means we want to minimize this area, okay, as much as possible. Okay, so if you want to minimize this area, so that means we can minimize it by decreasing the coercivity field. This is our HC, coercivity field. So the goal is low HC. So that is what we want in the material. So low HC is normally it happens when you have a low anisotropy. So if you take a material with a low anisotropy, magnetic anisotropy, so then you can decrease HC and you can minimize this hysteresis loss. Of course, this does not depend on the frequency. And then another way is to reduce your eddy current, because that is basically your I square PCR, which you have to reduce. And to do that from a material point of view, you want that your resistivity of the material is high. So that means high. So if you take a material like conductor, so eddy current loss will be higher. But if you take an insulator, a magnetic insulator, so then you will have a very low eddy current loss. So in that sense, so there are many different materials which I will just write down the list. So what is so the most common material that is used in transformer, or for that matter in most of these electric devices, that is known as electric steel. Okay, so steel means it is majorly you have an iron component mixed with either carbon or it could be silicon. So there are different kinds of steels you can get. So So of course there can be some other impurities as well, but primarily these are the components. Okay, so iron plus carbon or iron plus silicon. So these are like the alloys we discussed. So now when you make these alloys, so there is a process called crystallization. Okay, so I talked about the crystals or the atomic arrangement of the alloys, right, or any material for that in that sense. So what? So let's say just briefly I can tell you. So if you take a liquid, okay, and when you cool it down, so you get, or let's say you take water, so you cool it down, you get ice, so you get a solid material. So similarly, when these materials are made, these different alloys are made, so you go to like the liquid state, so you really melt it, and then you cool down, and you get so an alloy with different composition depending on what you mix and so on. So from a liquid state, so you do a controlled cooling and you get your solid. So which is called mostly to be a crystalline material. Crystalline means it has a regular arrangement of atoms. So the atoms are regular or a periodic arrangement. And that gives rise to crystal. And so this crystallization process, in this process you can control most of the parameters which are going to affect your hysteresis. So hysteresis you can define or you can control or manipulate by this crystallization process. Okay, so this is so one of the way how you can so in metallurgy, so you can control how you make these alloys, how you cool down, how you crystallize, and that is going to affect the properties, magnetic properties. So it is not only for magnetic properties, so also it is for any other its mechanical properties or its electrical properties. Everything you can control actually during this crystallization process. So for example, if I, instead of cooling down slowly, if I cool down it fast, so in the crystallization or in this process, so if I say fast cooling, so this fast cooling has a term, it is called quenching. So if I quench, so you get a amorphous material or like a glass. Okay, something like glass. So you can get glass or amorphous material by this fast quenching. So because so the process is basically, so the atoms need some time to arrange in a certain position. So if they do not do that, so it will become amorphous. There is no long range order, there is no periodic order. But in this process, so since you cool down very slowly, so there is enough time for the atoms to move and position themselves at they can go to their proper seats or proper positions, and you get a long range ordered crystal. Okay, so these two mechanisms, in both these ways, you can also manipulate the magnetic properties. So for example, in crystalline material, so you will have, so if I take the same alloy, A, B as alloy, and I have crystalline when the magnetic anisotropy is high. Now, if I take amorphous material, this anisotropy is small. Okay, so by using your crystallization process, how fast or how slow you cool, so you can actually get different anisotropy, and that is going to affect your coercivity. So here you will have a low coercivity because you have low anisotropy. Okay. So in soft magnetic, there are many different soft magnetic material. It could be a crystal or it could be an amorphous as well. So depending on the price or how easy or difficult to process it, so for different applications, different amorphous, different soft magnetic